Okay, the last method we're going to talk about is the master method. It means that instead of trying to solve the equation, we obtain our conclusion directly from those theorems called master theorems. So this is the first version of the master theorem. It looks quite complicated, so I would suggest you to pause the video and take a minute to go through this theorem by yourselves first. So see, basically we start from this recurrence equation obtained from, say, divide and conquer. And the conclusion depends on the relationship between this f and this term of n to the power of log a over b. So it actually depends on which one is larger. In the first case, say this f of n is bounded above by this term and something that is a little bit less than this term. So which means this term is larger than f of n, and therefore the conclusion will be big theta of this term. All right. And in the third case, where f of n is bounded below by something that is a little bit larger than this term, means f of n is bigger, and therefore the conclusion will be big theta of this f of n. And of course, we need to check an extra condition called the regularity condition, but that's not a big deal. Anyway, when these two functions are equivalent, in the conclusion we're going to have an extra log n here. Now let's check how it works. For example, for merge sort, in the recurrence equation we have like 2 times t of half of n, right? And therefore a equals b equals 2. And that fits in case 2 because log a over b is just 1. So this function is just the linear function n, right? And in merge sort, it takes a linear time to merge the two sorted sublists, right? So that means this function is indeed big theta of n, so they are equivalent. And therefore we obtain the conclusion like n times log n. That's case 2. Well, although it's called master theorem, still it doesn't mean that it can cover all the cases. For another example, if a equals b equals 2, this term is just n to the power 1, right? But what if f of n is n log n? It doesn't fit into any of the conditions, right? Let's check those conditions one by one. Certainly is not bounded above by n to the power of 1 minus epsilon, because this is more than n, it's n times log n, so condition 1 doesn't work. And for condition 2, this is big theta of n, this is n log n, it grows faster than n, so condition 2 doesn't work. And for condition 3, it's bounded below by n to the power of 1 plus something. In other words, does it mean that log n is bounded below by n to the power of some epsilon? And therefore to conclude that t is big O of n log n? And the answer is no, that is not correct. Because what? Because log n grows so slowly that it grows slower than n to the power of any number. All right? So it just means that we cannot obtain any conclusion based on this master theorem. We simply don't know. Okay? So again, although this is called master theorem, it doesn't cover all the cases. The next, let's see how to prove it, just as a kind of practice. Right? Let's try to prove by recursion tree. Here we assume that n is b to the power of k for some integer k. It just means that we can keep dividing n by b, and always obtain integers until we get 1. All right. So this is the recursion tree corresponding to the problem. So we're going to start from T of n. And T of n will be broken into f of n plus a branches. And each branch corresponds to a problem with the size n over b, right? And then that T of n over b will be replaced by f of n over b plus another a branches. And we just keep going like this. Keep dividing n by b until we get a constant at the bottom level. So everything is just similar to what we have done in the previous examples, right? So the height of the tree is obviously log n with base b, right? And at the bottom, we're going to have n to the power of log a over b, that term, that many leaf nodes. So the time complexity for the last level is big theta of n to the power of log a over b. And then besides the bottom level, in other levels, we're going to have f of n, a times, there are a branches, right? A times f of n over b, and then next is going to be a squared times f of n over b squared, and so on and so forth. And therefore obtain this total sum of all the complexities. And we're going to have big theta of this term, that is the bottom level, plus this sum. Okay, now let's take a closer look at this sum. So for case 1, we assume that f of n is bounded above by n to the power of this term minus some positive epsilon. Okay, and this sum is going to be what? Plug this one into this form. So that is to substitute each n by n over b to the power j. And therefore we get this one is big O of, now replace this n by n over b to the power j, and this is what we get. This is big O of this sum. Alright, now let's try to simplify it. First of all, we realize that n to the power of log a over b minus epsilon, this term has nothing to do with j, and therefore it's a common factor and can be factored out. Alright, and this is what we get. And simplify the rest of the terms, we get that this is actually just a, right? And therefore this a and this a will be cancelled out. So this is simply b to the power of epsilon then to the power j, right? So this is what we get. And this sum can be obtained by using the formula that I assume that you have learned in high school, right? So after calculation, we get this one and simplify this. This part is just n to the power epsilon. And the rest is only a constant, so it's in big O. And therefore we get big O of n to the power of log a over b minus epsilon, then plus epsilon. So they will be cancelled out. Therefore obtain big O of this term. So finally we get T of n is big theta of this one, that is for the bottom level, and plus this sum gives an upper bound of big O of this term. So put them all together as big theta of this term. That completes the proof for case 1. And as an exercise, I would suggest you to try to prove case 2 by yourselves. It's not very complicated. It's actually quite similar. It will be interesting to see where we can obtain that extra log n from. Alright, and the complete proof can be found from the book Introduction to Algorithms in the chapter 4. Alright, this is the well-known master theorem, but it's in a quite complicated form. We have another simplified form for the master theorem. So it looks much simpler, right? So the key is to compare this one with f of n itself. This one is what? This is to replace t by f. Okay? Compare these two functions. If this one is a kappa times f, where this kappa is a constant which is strictly less than 1, it means that f of n is larger than this one. And therefore, the conclusion is going to be big theta of f of n. And if this one is a big K times f of n for some constant that is strictly greater than 1, it means that this function is larger. If this one is larger, then the conclusion will be big theta of n to the power of log a over b. And if they are equal, exactly equal, then the conclusion is going to be f of n times log n with base b. Alright, so it looks much simpler. But again, same as the previous master theorem, it cannot cover everything. Now let's see. For example, if a equals 4 and b equals 2, then what is this? That's log 4 with base 2. That gives 2. So this term is going to be n squared. Right? If this term is n squared, but f of n is n log n, what can we get? Now let's try to compare like 4 times f of half of n with f of n itself. So what is this? This is 4 times f of half of n. So it's 4 times replace n by half of n. So we get half of n times log half of n. And simplify it, we get something like 2n times log n minus log 2, where log 2 is 1, right? So we get 2n log n minus 2n. And compare it with f of n, which is n log n. So obviously they are not equal, but we simply cannot find any single constant to make them equal. Okay, there's no way to make them equal because there's an extra term here. Right? So it just means that we cannot apply this master theorem to obtain the conclusion for this case. But if we apply the previous form of the master theorem, can we get to anywhere? Well, let's see. So this is f of n. And this is the term of n to the power of log a over b, which is 2 minus epsilon. This is big O of n to the power of 2 minus epsilon. Are they equal? Think about it. Well, so first of all, we can cancel 1 n and just compare log n with n to the power of 1 minus epsilon. So it's like n to the power of 0 point something, right? But anyway, no matter what that number is, it's a constant. It's n to the power of some constant, right? And we know that log n is always bounded above by n to the power of any constant. And therefore, this is true. And they are equal. Which means what? Which means this case fits into the first case of the previous master theorem. And the conclusion will be what? This term is larger than f of n, and therefore the final conclusion will be big O of this term, which is big O of n squared. Right? So this is one example to show you that there are some cases that are not covered by this form of the master theorem, but can actually be solved by the previous form of the master theorem. Okay, but after all, none of them can cover everything. So for the previous example where a equals 2, b equals 2, and f of n is n log n, it can be covered by none of these two forms. But fortunately, we have yet another one. And this is the theorem for a more specific case. a recurrence equation with a very special form for that f of n. If f of n is in this form, then we may have one of the three conclusions. It depends on the relationship between a and b to the power k with this k. So for example, for merge sort, we have a equals b equals 2, where p equals 0, so we don't have this term, and k equals 1. That's big theta of n to the power 1. That is the case for merge sort, right? And let's check this relationship. We can see that a equals to b to the power k. So it fits in the second case. And therefore, the conclusion will be big O of n to the power k. That's 1. That's n times log of n to the power of 0 plus 1. That gives n log n. Alright, so that is true for merge sort. And let's try another, a more complicated case. Say we divide with a equals 3, b equals 2 for each recursion. And then let's conquer with a linear time, which means k equals 1 and p equals 0. Okay, so a equals 3, b equals 2, which means 3 is greater than 2 to the power 1. So it's in case 1. And therefore the conclusion will be big O of n to the power of log 3 with base 2. So you see that's where we obtain those strange exponents like 1.59. And on the other hand, it all depends on the conquer now. If conquer takes n squared time, then it means that k equals 2 and p equals 0. That's going to give us the third case where 3 is smaller than 2 squared. And therefore, we're supposed to obtain, well, p equals 0, so we don't have this term. We're supposed to obtain n squared here, n squared. All right. Now finally, let's check the previous hardest case where cannot be covered by those master theorems. Well, if a equals b equals 2 and f of n is n log n, that means k equals 1 and p equals 1. And a equals b equals 2 corresponds to this case, right? 2 equals 2 to the power 1. And therefore, what we get is this conclusion. It's big O of n to the power k. So k is 1, so it's n times log p plus 1. So log n squared. So the final conclusion is going to be n times log n squared. Okay, so much for divide and conquer.